Oh, let's move on to the next topic about the complement probability, right? The complement. Complementary probability. Right, so the Venn diagram of the universal sample space and then event E in the middle, right? That is the event E occurs, the circle, right, is the event E. So what we can do is we see the denotes the EC denotes the complement of event 2E. Complement to event E. So in other words, the E complement occurs means the event E not occur. Why do we have complement, right? So the entire rectangle is the event of sample space, and inside the circle is the event E, and this big part here is the event of E complement. And the sample space together is formed by E and E complement. Right, so the event E union together with the event E complement is our sample space, and the intersect together is empty. Right, that notation is called the union. Intersect is the intersection. That is the U or upside down U is the union and the intersection. Right, which means the complement union with the original event will be the whole sample space, and intersecting together is the empty set. Right, this is the empty set, or called the null set. Doesn't have anything. The criteria is the probability of E plus the probability of the complement event equals to 1. Right, so if sometimes the E complement is easy to find, we can find the E by 1 minus the E complement. If sometimes we need to find the complement event and the original is easy to find, we're able to do that as well. 1 minus the E, probability of E will give us the probability of its complement. And of course, if the case that both are required, then to find one of them, then it will be good enough to find the other. I just use 1 minus. Well, let's see some example. This is an 8 to help us to find the probability. Sometimes maybe in the question it's not clearly identified which to use the complementary probability. I denote the number, the face of a die shows when it lands. find the probability that x is 1, x is even, probability that x is not even, probability of x equals 1, and probability of x equals or greater than 2. Right, to find this probability, right, these four. The first one saying probability of x is even, right, if we know the sample space of rolling one die, right, the sample space, if you want to write down, that's 1, 2, 3, 4, 5, and 6. So for the probability to be even, that's 6 numbers in the die, when we roll it once in the sample space. To be even, that's 2, 4, or 6, that's 3 of them, which will be 1/2. And then for the probability it's not even, since we found the probability is even already, we could just do 1 minus that. Right, so 1 minus the probability to be even, that is 0.5. Right, this is the case while we could apply the complementary. Right, and it's not necessary that we're always able to find it straightforward. Right, that if x is not even, then x to be odd, we get 1, 3, and 5 are odd numbers. That is also 3/6. Right, then apply that is also appropriate. To straightforward is also appropriate. Right, the outcome to be 1, that is 1 out of 6. To be at least 2, that just exclude the 1. Right, so the complement apply. Right, greater than or equal to 2, that is 1 minus the probability of x to be 1. One minus the result we found already, 1/6, that is 5/6. If you observe the original sample space to be 2 or more, that's 2, 3, 4, 5, 6. That is also can be seen as 5/6. Right, this is simple enough, but when we get to harder probability, things may be getting harder and more tricky to do, right? Then apply the rule of complement will be a very good aid to help us. Rolling 2 dice is also a classic fact question. If y denotes the sum of the results of the face value, by simply rolling 2 dice, I also provide the sample space how it looks like to roll 2 dice, right? The sample space, that is, well, the first could be 1, the second die could be any number from 1 to 6. That's when the first die is 1. The first die could be 2, and the second die is varying from 1 to 6. And also the first die could be 3, Right, the first die could be 3, or could be 4, could be 5, could be 6, right, all the way. Right, when the first die is 5, it could be also second die could be varying from 1 to 6. And the last possible is the first die is 6. Right, this will be the entire sample space of rolling 2 dice. Right, I gave you out this thing on the table on the picture I found out. Right, then actual question. Right, the question asking to find the probability that the sum is equal to 1, probability that the sum is between 2 and 3 included, probability that the sum is 4, or the sum to be 7. Right? Well, when we observe the table, right, we can see that 2 dice we have the sum is, well, at least 2, right? Then 1, 2 and the 2, 1 will have the sum to be 3. And 1, 3, 2, 2 and 3, 1 we have the sum is 4, and so on. Or the diagonal will give us the sum to have same value, such as 1, 5, 2, 4, 3, 3, 4, 2, and 5, 1 will give us the sum to be 6, right, and so on. So it's impossible to get the sum to be 1 unless you destroy one of the die, which is one of the dice, which is impossible. Right, so that is 0. To have 2 or between 2 and 3, that's simply just to have the sum is 2 or is 3. Right, the sum is 2, we get just one value, 1, 1 only. The sum to be 3, that's 1, 2 and 2, 1. So that is 3 out of the 36 outcomes, 1/12. Right, for the sum to be 4, we get in the sample space, we get 1, 3, 2, 2, and the 3, 1. That is 3 out of them. Right, 1/12. The sum to be 7, that we have is 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and the 6, 1. That we have 6 of the outcomes, right? 6 outcomes inside the sample space have the event that's the sum to be 7. So you get 6 out of 36. Well, if you count in total, that's 36 different outcomes in the sample space. And 1/6 is the probability to get the sum to be 7. Right, so that's when we're rolling 2 dice and the sum. Right, the question could be asking more, but well, we'll see then. Also, to find a card, right, randomly select one card. from a deck of cards, find the probability of getting a spade, getting an ace, getting a red card, getting a black card. Right, for the deck of cards, well, we have 4 suits, right? The club, the club, and the spade. And the heart. Club, spade, heart, and diamond, 4 suit, right? The clubs and spades are black cards, hearts and diamonds are red cards, and each one is numbered from 1 to 10. It's not 1. It's ace, 2 to 10, and then jack, queen, and the king. Right? Each has 13 kinds. 13. Each suit has 13 cards. And ace is ace, 2 to 10 are 2 to 10. Jack, queen, and the king are face cards. Right, that's 13 times 4, which give us 52 total cards. Right, so to get the spade, the probability of getting a spade, that each suit is 13 cards, right? 13 out of 52 cards, which is a quarter. To get an ace, right? To get an ace, that the ace is occurring at each suit, so that will be in total 4 suit, right? 4 suits, therefore we have 4 aces: ace club, ace spade, ace heart, and ace diamond. That is 4 out of 52. Is 1/13. Probability of getting a red card. For 52 cards in total, that we get 26 of them are red, right? 13 each. 2 suits, that's 26 of them. Which is a half. Well, the black card is similar. To get the probability of black, when the red is a half, the probability of red, that is 1 minus, the probability of black is 1 minus the probability of the red card, which half is red, half is black. The other half. 1 minus a half is also a half. Right, so that is the deck of cards. Right, then we go to the compound event. Combining two or more simple events. Right, the entire sample space and the event E and the event F. Right, the middle intersection part is that piece that both E and F occurs. So we could consider that as probability of E and F. Right, both the E and F occurs. Intersection of E and F. So for instance, right, to get a red card and get an ace, which means that we will get an red ace. Right, to get a red card has probability of a half. Get an ace will get probability of 1/13. Right, but to get a red ace, that will be 2 out of 52 only. That is 1 over 26. Right, so that is type of intersection of two cards. I mean of two events. The E and F, we just consider the condition together, right, to view the event or to view the outcome that satisfy both of the conditions. And for the big piece here, that E and F occurs all together, two circles, that's E or F occurs. It's like not usually saying the or, right? It's like all together. The or means either, not either. That all means event E or event F occurs. That combination could be work enough. Written as probability union. Usually we say E union F, the union of two events, which means E occurs or F occurs. That will count as the total entire shaded range. Right, and the addition rule says that if we want to compute union F, what we do is compute the E plus the probability of F minus the intersection. Right, we could see the diagram. if we separate it into two pieces, right? The first, the second, and the third. Each diagram, each event separates into three pieces. Right? The probability, the union is supposed to be 1 plus 2 plus 3. While the E part, E is the first part plus the second, F is the second plus the third piece. Right? When we combine the E and F together, that is 1 and the 2 and the 2 and the 3. What we need to do to make sure that they are equivalent is we need to take out of the intersection part, which is the middle piece. We take out the middle piece, that we get 1, 2, and 3, which is appropriate. Right? So that is the addition rule. Right? So this is the addition rule. And for the special case, disjoint events or mutually exclusive events well, disjoint is literally clear that the two events has no overlapping. Right? No overlapping. No overlapping, that the intersection is never happens. Right? That is the true criteria. Therefore, for no overlapping, for disjoint events, the union if we apply the power rule, right, the addition rule, that actually has the intersection part goes to 0. It actually has the intersection part is equal to 0. Therefore, if we know two events are disjoint, we can just add their probability separately, and that is good enough. Right? That means that they cannot occur at the same time. Either E occurs or F occurs. Right? That is the disjoint events or mutually exclusive events. How we determine that two events are mutually exclusive is in the case that their intersection equal to 0, or is another case that the union has a probability equals to sum of each part. Right? That's how we distinguish if two events are mutually exclusive. Right, so let's see the example. Still the drug testing. Uses drugs, not use drug. Positive result, negative result. Have 44, 6, 90, 860. And we found already the total was 134, 866. From the row is 50 and 150. Overall is 1000. Right, that's we have found already. The row total, column total, and so on. Right, so question is, if one subject is randomly selected, what is the probability that selecting subject has a positive test result or uses drugs? So we have that question, right? So it's a positive test result or uses drugs. Intuitively, we can observe the table that while 40 and 90, those people are positive test result. And for additional 6, they are uses drugs. 40 and 6 are uses drugs. That we have 40 people are positive and uses drugs. 90 subjects are positive but not uses drug. And also together with the 6 subjects are uses drugs but have negative result. All of them 3 criteria follows the condition that positive test result or uses drugs over 1000. And that is how many? That is 140. Right? Intuitively, that makes sense. If we want to use formula, the probability of positive test result or uses drugs, that is the probability of positive test result plus the probability of those who uses drugs minus the intersection of positive and uses drugs. Right, that's use formula to get positive test result or uses drugs. That follows into 2 conditions, right? Positive result or uses drugs minus the intersection. That is 134 of them have positive result. 50 subject uses drugs. Intersection, that's positive and uses drugs, which being added twice if you consider from the table. Right, so we need to take away that, which is still 0.14. Right, so the formula holds when we do intuitively or in the formula, it should give us the same answer, right? So for the two-way table, we could use the intuitive way or use the formula. You are free to choose. For some question, maybe formula will be a little easier. Right? Intuitively, to find the union is not that easy in the usual other type of questions case. Right, let's see the next example. one card from a deck of cards. An ace, diamond, spade, red card. So find the probability that the select card is an ace or is diamond card. Probability select is an ace, spade, or a red card. Right, the selected card is an ace. The selected card is diamond. The selected card is a spade. The selected card is red. Right, for those letter, right, that means. And while we exist in ace diamond, right, so before that, so we find the union, we could observe it, right? Would there exist an ace diamond or a diamond ace? So we use the formula to do probability of getting an ace, probability of the card is a diamond, minus the probability is an ace and it's diamond. Right, we have the sample space you can find. From that, there are 4 aces. Diamond is a suit, contains 13 cards. There is only one card, which is the diamond ace. So we get 4 plus 13 minus 1. That is 16 over 52. Or 4 over 13. Or you could simplify that if you want to, but at least show me this 16 over 52 as the result. You could divide them into decimal. That's about 0.3077 is also appropriate. But just please show me the 16 over 52 and show me the setup. Right, the probability of to get the spade and the red card, or the spade or the red card. The spade is black, the red card has 2 suits that are red. So this one is disjoint. Therefore, the probability of union will be just direct sum. We'll have 52 cards. There are 13 of them are spades. And the red cards contain diamonds and hearts. Right? 26 cards, which is 39 over 52. That is 3/4. If you want to show that is 0.75. So this is the example using the addition rule. The addition rule of the case that we use select the deck of cards. Of course, that's just the example. Things could be and should be asking for different questions. Could be easy, could be hard. So that's what it is. Right? And we see some more example next time. All right, thanks for watching. I'll see you next time.